Welcome to part one of the fundamental theorem of calculus. I will describe the theorem and prove it. Part one of the fundamental theorem of calculus is about a Riemann sum area to the right of a fixed vertical line at t equals L underneath a curve f of t, and to the left of a vertical line at t equals x. We should consider this area as a function of the position of the rightmost vertical line bordering the region, which would be at t equals x. Specifically, the theorem states that the rate of change of this area per unit change in x is equal to f of x. A simple example of this is that the rate of change of the area of a rectangle per unit increase in length is equal to the width of that rectangle. In order to prove this theorem, we will start with the extreme value theorem, which is for functions continuous on a closed interval of the real numbers. It states that there exists at least one domain value x of little m and another x of big M in the domain, such that f of x of little m is less than or equal to f of t, and f of x of big M is greater than or equal to f of t for all t on the interval. We'll call f of x of little m, and f of x of big M, and then we can restate this theorem briefly as f of t is greater than or equal to little m and less than or equal to big M everywhere on the interval. And in fact, the function takes on the value little m and big M on the interval. Notice that the function would still be continuous on a subinterval of our original interval, and so the theorem would hold on a subinterval, say, from x to x plus delta x. It is a property of Riemann sum areas that if one function is larger than another on an interval, then its Riemann sum area is larger than the later on the interval. And so we can write this inequality between Riemann sum areas based on the compound inequality m is less than or equal to f of t is less than or equal to capital M. Notice that the area at left and the area at right are each rectangles, and we can evaluate them fairly easily. It will then serve us to divide by delta x. A property of limit states that if one function is greater than or equal to another on a domain, then the limit as the domain variable approaches any value in the domain of the larger function is greater than the limit of the lesser function. And so we can write an inequality between these limits based on the compound inequality between these three values. Notice that little m and capital M are the minimum and maximum values of the function, respectively, on the interval from x to x plus delta x. As this interval shrinks, that is, as delta x goes to 0, then m and capital M, as well as all other values of the function over the domain from x to x plus delta x must approach f of x. So we can replace the value at left and the value at right, each with f of x. Now we have a limit which is greater than or equal to f of x and less than or equal to f of x, and so we can rewrite this compound inequality as an equation. Notice that the area in the numerator on the left side of this equation can be rewritten according to a property of the Riemann sum areas. And we can replace the area from x to x plus delta x with the area from L to x plus delta x minus the area from L to x. Notice that we now have on the left side of this equation the limit of as delta x goes to 0 of the area out to x plus delta x minus the area out to x all over delta x. This is the derivative of the area out to x. This final equation then is our original statement of part 1 of the fundamental theorem of calculus.